posterior over here, I can say all the landmarks are independent of each other because I know where the system was at every point in time. Okay, so landmark variables are kind of disconnected, so they're independent given the robot's graph. Okay, so I know that here these landmarks are independent of each other now, given the poses. So I can split that up into a product of probability distributions over the individual landmark locations. So this turns into a product over m landmarks, p of mi, so that's not the individual landmark, given the poses and given the observations. In which way is this a dramatic simplification to go from here to here? Why is it substantially easier to do it this way compared to that way? Yeah.
We can compute each landmark separately.
Exactly. And if you think about EKF, for example, to compute the location of a landmark, that this means we have to maintain m tiny, small 2 by 2 Kalman filters for every landmark individually. And this would mean we would have a large, giant 2m dimensional covariance matrix using a 2m dimensional EKF. So instead of using a one high dimensional EKF, we use a large number of low dimensional EKFs. So, and therefore, this is substantially more efficient. So all these guys here are now 2 by 2 Kalman filters, or EKFs. Every landmark, location of every landmark can be easily estimated on its own, independently of the rest, given I know the poses. So every sample, because every sample says I know where the robot was, that's the assumption of each sample. Because I know where I was, I can compute every landmark individually. So every sample can maintain m small, tiny 2 by 2 Kalman filters and estimate the location of each landmark in a very, very effective manner. Okay, to sum that up, we have this posterior here, which is of which we want to use a particle filter, and this is somehow similar to MCL, to Monte Carlo localization, because we want to estimate the trajectory of the robot given our observations, given our controls. The only difference is we don't have a given map from the beginning on, but the key trick is we can build up this map incrementally because we have our mapping process over here, which is independent for each sample. And so every of those samples which is used to represent this posterior gets a map associated, which is built individually for every individual landmark. That's kind of the key insight here. So is the basic principle on how we're trying to tackle this LAM problem clear to everyone? If not, please ask me now, because we'll be getting a little bit more involved within the next 1 hour. So would like to make sure that you understood the concept up to here.
Just one question.
Yes, sure.
What will start from the same position at the beginning?
Yes, typically. So typically what you do is, if you think about a practical application, you fire up your robot and you start kind of with a local reference frame. Every particle says, okay, I'm in the robot's world reference frame at 0, 0, 0. And then we start from this point on. That's typically the way you do that. If you have a different application that you directly want to start in a global reference frame, and you have an initial belief, you can distribute the samples according to this initial belief. That's basically up to you. The standard particle filter, we say, I don't have any external frame, I just want to estimate what the map looks like. Then you start, all the particles start with the same pose with 0, 0, 0. But if you want to do, for example, you want to start giving a GPS reference frame because you want to relate the robot's trajectory directly to a map and maybe want to exploit this map partially during the mapping process. And you have, let's say, an initial distribution about where the robot is. You can use those samples to represent the start belief. You may need more samples in the beginning, depending on how large your initial uncertainty is. But most implementations start at 0, 0, 0. But it's kind of an easy extension if you want to use an initial uncertainty. Any further questions? Okay, perfect. So let's dive a little bit into the details and start with this guy over here. How are we going to do that? So we said we want to use a sample-based representation to represent this first part over here. So this guy should be represented with our samples. So how do these individual dimensions look like? So we have a starting location x0, and this is exactly refers to your question. We typically start with 0, 0, 0, unless we have some reference to an external frame. And then x1 is the pose of the robot x at time t. x2 is the pose of the robot at time t equals 2, always the xy theta location. However, in this particle filter, we never revise the path trajectory. So we never say, okay, at that point in time in the past, I did a mistake, so I correct all the samples. That's nothing which a particle filter does. So it always takes it a step forward and estimates the next trajectory of the next position of the robot. So as a result of that, in practice, I don't actually need the past trajectory of the robot because on the fly, build a map on the fly. I'm only interested in the next pose. So I can actually, I do not actually need to maintain the previous positions where the robot was in my sampled belief. So as a result, there's in the sample set, I only represent kind of the current pose of the robot because the past is not revised. I could, in theory, let's say, dump them somewhere to disk in case I need it. Typically, implementations do that because they want to draw the trajectory in the end. But for the mapping process itself, I don't need that for the estimation problem I'm facing here. So in practice, every particle only needs to maintain 3 dimensions for the pose and then 2 times m dimensions for the landmarks, whereas every landmark is a 2x2 Kalman filter. So that's exactly how the first efficient implementation of a so-called Rao Blackwell-ized particle filter for SLAM looked like. Every particle has an x, y, theta dimension, so current pose, an x and y and orientation, landmark 1, landmark 2, landmark 3, and these guys are my 2x2 Kalman filters. And Mike Montemello, 2002, was the first one who actually came up with exactly this representation and with an efficient way for implementing that. So it was kind of the first implementation of a Rao Blackwell-ized particle filter that could handle large maps or real-world problems. So kind of the first successful implementation. And actually parts of these slides go back to Mike in here, or some of these animations, especially this one over here. So this is an example. So these are, let's say, our simplified world with only 3 samples. In reality, of course, we have more. So particle number 1, 2, and 3. Particle 1 says, okay, the robot is here. Particle 2 says the robot is here. And particle 3 says the robot is here. And these are the corresponding landmark estimates, maps of those individual samples. And these are all these 2x2 Kalman filters. So what happens? The robot moves. So this one said, okay, the robot moved over here. This one said the robot moved over here. This one, the robot moved over here. This new position is generated with the proposal distributions, which is equivalent to the localization problem. So I just use my odometry motion model to draw the next pose. And the next step, which needs to be done, is the sensor update. So I need to take into account my sensor information to update my belief, to compute the importance weight. How can I do that? I just, let's say, this is the observation, so 2 landmarks. And I say, okay, this robot would observe 1 landmark here, 1 landmark here. This robot says, okay, 1 landmark is here, 1 landmark is here. And this says 1 landmark is here, 1 landmark is here. So what I need to do now is I need to take into account these observations excuse me, and turn them into importance weights. And you can see this important weight. We will derive it later on, why it is exactly what I will show you in a second. But you can use this kind of, if I talk quite informally about that, it's kind of an evaluation. How well did the particle in estimating the map given the current sensor observations? So how well are the current sensor observations in line with the map that this individual particle built? So if you think about over here, that actually looks pretty close. So if, let's say under the assumption that this observation corresponds to this landmark and this observation corresponds to this landmark, that looks kind of reasonable. Here we are much further away from our estimates. So this particle will get a high likelihood and this will get a probably quite low likelihood. And this one, this landmark, this observation is pretty far away from that landmark, also will get a quite low likelihood. So And this is exactly what happens. We can compute